Capacitors in circuits 2. So based on this figure, we want to calculate the following quantities. Feel free to stop the video and try and solve this on your own. I'm going to go through it rather quickly here. We don't have to do these in any particular order. Whatever way is easiest, we're going to do it that way. So let's see if we can find the equivalent capacitance. I'm seeing these two capacitors here in series with each other, and that section of the circuit is in parallel with this. These two are in series, and then this is all in parallel. Let's find the equivalent capacitance of this portion right here. If we were to tear those two out and just put one capacitor there, what would the capacitance be? They're in series, so we'd need to use the 1 over equation. 1 over 9 plus 1 over 18. You can do the math if you want. 6 nanofarads. If we tore those two out and just put one there, it would be a 6 nanofarad capacitor. This one, same idea. 1/12 plus 1/12, add them up, flip it upside down, 6 nanofarads right there. That imaginary 6 is in parallel with this real 18, with this imaginary 6, and with this real 6. And whenever you have capacitors in parallel, you just add them up. So that's going to be 24 plus 12, 36. 36 nanofarads. That's the equivalent capacitance. Now, many times we've gone through this equation that capacitance is Q over V, and so the total charge can be found if we rearrange this equation as the equivalent capacitance times the voltage of the battery. The equivalent capacitance is 36. The voltage of this battery is 6, so that's going to be 216 nanocoulombs. The nano prefix hasn't disappeared. All right, now what do we do? Well, what I like to do at this point is I like to color wires with voltages. We will talk about this a lot more when we get to what I call circuit Sudoku problems, but any portion of a circuit that is connected with wires like so, every portion that I'm drawing here has the same electric pressure, it has the same voltage. All of those points have the same voltage. Same thing on this side. All of these connected wires that I'm coloring green have the same value of voltage right there. These two portions in the middle that look like a capital H, we don't know what those voltages are. We know this top H is all the same voltage. We know that this bottom H is all the same voltage. They're probably not equal to each other, though. However, if red to green is 6 volts difference, which it is because this is a 6-volt battery, and this side of the battery is that color, and that side of the battery is that color, that means that the voltage across capacitor C is also 6 volts. And the voltage across capacitor 6 down here in the bottom is also 6 volts. All right, well, capacitance is Q over V, so Q is going to be C times V. Q6 is C6 times V6. And strangely, that comes out to be 36 nanocoulombs. Same thing up here. Q3 is going to equal C3 times V3. Well, C3 is right here, 18, and V3 is 6. 18 times 6 is 108 nanocoulombs. Okay, well, now what? Well, we can use this idea of this pretend capacitance. If we took this whole thing here and put one capacitor there, it would be a 6 nanofarad capacitor, and the voltage across that 6 nanofarad capacitor is 6 volts because it's red on this side and it's green on that side. So this imaginary capacitor has a voltage of 6, which means the charge that's on it is this imaginary capacitance, which is 6, times the voltage across it, which is 6, which means that the charge on capacitor 1 is 6 times 6. Put a little double asterisk by that one. We had to do a little thinking there. And capacitors in series have the same charge. So that means capacitor 2 is also going to be 36 nanocoulombs. How about down here? Same thing. This is an imaginary 6 nanofarad capacitor. The V across it is 6. So the charge that's stored for C4 and C5 is going to be 36. We had to do some thinking there. That's why I put an asterisk by those. V is equal to Q over C. So V1 is Q1 over C1. So that's going to be 36 divided by 9, 4 volts. V2 is going to be Q2 over C2. That's going to be 36 divided by 18, which is 2. Hey, look at that. You see that? 4 and 2. That's the voltage across here. 4 and 2. That gives us our total of 6. All right, we got 2 more boxes to fill in. Here we're going to go V4 is going to be Q4 over C4. C4, huh? 36 divided by 12, 3 volts. V5 is going to be Q5 over C5. 36 divided by 12, 3 volts. Once again, there's our 6-volt difference across that part of the circuit. All right, what's the total energy stored in this system? We could calculate the energy stored in each of the 6 capacitors and then add them up, or the quicker way to do it is to say that the total energy is going to be 1/2. You can use any number of equations. How about the equivalent capacitance times the voltage of the battery squared? 1/2. The equivalent capacitance is 36, and the voltage of the battery is 6 squared. Okay, and that's going to be 18 times 36. Ooh. Do I have a calculator? I don't. 36 times 18. Let's do it. 648. 648. And the 36 had nano with it, so this is going to be nanojoules. 648 nanojoules. If you found the energy stored in each of those 6 capacitors and added them all up, boom, that's what you'd get, 648.